Hey everybody, Mr. Newland here. We're going to talk about using Gauss's law to find the E field near a infinitely big uh, charged plate. And really this is a lead into capacitors again. When we talked about E field near a charged disk, I'll remind you that we ended up showing that if you're close to the disk, or if the disk is really big compared to your proximity to it, whichever way you want to think about it, then you end up with another near field approximation, meaning that if you're an electron and you're in the region somewhere close to a charged plate that's even remotely big, so like a centimeter or more, then from the standpoint of the electron, that charged surface is infinitely big. So we're going to expect to find something similar here. So let's start with Gauss's law. Once I get the pen to write. So the flux, the electric flux through a closed surface. And you can see here they've drawn this closed surface. Now in class I mentioned a pillbox idea, and sometimes I talked about it being on the surface and sometimes not. But now I want to be complete. Imagine that this or I guess I want to be complete. I want to be clear. So imagine taking this Gaussian surface, this cylinder, and even though the plane is infinite in size, so we're going to, like, theoretically, I guess, cut through it. So it's like a cookie cutter, okay? So imagine this cylinder that we can push through the charged surface. And now there's an area there. There's the length of the cylinder here. Part of it you can see, part of it you can't. And there's another area there. Okay, so let's think about the field lines coming out of this charged surface. Remember, the surface, or the plate, this thing, is infinitely big. And it's positively charged, so the E field's out at all points. Okay, so we can't see the edge of the charged plate from where we are, from the standpoint of this little perspective of an electron. Standpoint of this little perspective. I think I need more coffee, guys. Anyway, the E field is constant everywhere, and I want you to see that the E field right along this entire length of the cylinder will actually be parallel to the side, which means that the area vector from the perspective of the side of the cylinder and the E field, they're at right angles. And it's a dot product. Remember, this is the closed integral of the E field at that particular spot you're curious about. Dot product with the area vector differential element, so E dot dA. And remember, it's a closed surface. So, but much like we saw with the charged wire, part of this closed surface ends up being irrelevant. With the charged wire, it was the ends of the cylinder that didn't matter because the area vector and the E field were at right angles. Here it's the side of the cylinder where the area vector and the E field are at right angles, which means the only areas we need are the guy back there and the guy back there. So pi r squared there, pi r squared there. I'll remind you that the trick with Gauss's law is you usually can end up writing it as E times A. Remember, oh, I forgot to mention this in the last video, so I'll definitely do it now. Even though E field and the area vector are vector things, when you use a dot product, you lose that. So the flux is not a vector quantity. We end up with just how many field lines are going through our particular surface. And that's not always, like, that's still not necessarily a super intuitive idea. Like, what does that mean? And the whole point of using Gauss's law here is that we happen to know that E dot dA is the charge enclosed divided by epsilon naught. So if I can come up with an area and I can figure out what the charge enclosed is for that area, I can figure out the E field at that particular region. So, well, we know what the area is. We know that that's E times 2 times, times pi r squared. That was little r. I didn't actually indicate it, but the radius here, let's use little r. So pi r squared, but that times 2 equals Q enclosed over epsilon naught. Well, here's the deal with Q enclosed. Let's say that the entire plate there, that orange thing, I don't know why I always use orange, creamsicle orange. The entire thing is charged Q, and its entire area is A. All right? Well, essentially, they're infinite in size. Okay? So what that means is that we can consider it a constant everywhere. Remember, if there are a bunch of charges on this surface, they're going to spread out from each other as far as possible. So it's going to be uniformly distributed. So we're going to call that the surface density. Instead of the linear charge density or the volume charge density, we're going to call it the surface charge density. Lambda is what we use for linear charge density, rho is what we use for a volume charge density, and sigma for the surface. Well, for this particular area of space that we're curious about, the charge enclosed, Q enclosed, divided by whatever area we've got. So 2 pi r squared. Actually, wait. That's just for one of those areas. So pi r squared. Well, let's actually use this. This would be A total over there, and this will be A like they've labeled in our diagram. I realize that the textbook picture I stole here, they've already got an A. So back in our original example, the entire charge over the entire area, well, that's equal to how much charge that I've just surrounded with this surface divided by that particular area. That actually makes it a little bit easier to describe, and that's how I should have done it in the first place. Well, what that means is that I've got E, which is the thing I'm looking for. Gauss's law is often used to try and find the E field at a particular point. So E times the area, which is 2 pi r squared, is going to equal, so let's rearrange this. The charge enclosed is sigma A. If A is this little area here, not the whole thing, but just that, then that's Q enclosed. Well, I know that sigma A over epsilon naught equals the area. And we do a little algebra here, and what we end up with, so we know that this guy is sigma pi r squared, and that's epsilon naught. Remember, this was both areas from the top and the bottom of the cylinder. This is just the little area that we've got right there. That one little A inside there contains only Q enclosed, okay? So now we've got, let's see, pi's cancel, r squares cancel, and we end up with, make sure I don't mess up my algebra here, sigma divided by 2 epsilon naught. 2 sigma, yeah, that's right. So the E field, and again, we've got this, it's just the magnitude for this particular thing, but we know it's out at all points. So if we needed to describe it, we could say the E field at this point right here that I'm curious about, and this one back here, the E field at this point there and that one there is sigma over 2 epsilon naught. It's a constant. It is not, notice that E ends up not being dependent on how far away you are from the charge plate, which is the same thing we found when we did geometry consideration. So Gauss's law gave us one way to show that the E field is constant in this scenario, and we did the same thing with an integral before. So this is a very significant thing. It turns out we can use, when designing a capacitor, all kinds of things, actually, all kinds of electrical things. As long as two electrical surfaces are close to each other, you end up with an E field that's constant. And there are ways to use that to your advantage when you're designing things. This is not just a theoretical idea. It actually has implications. Okay? So I want to say another thing about this. One of the implications is a capacitor. And in the scenario here we're looking at the charge plate from the side, and you can see the E field is out at all points. Here you can see charge plate on this side is positive, and a charge plate on this side is negative. Okay? So this guy has an E field of sigma over 2 epsilon naught. This guy also has an E field of sigma over 2 epsilon naught. So the first thing you'd notice is that the E field due to this guy and the E field due to this guy end up canceling each other out everywhere outside. The only E field you end up with is inside. Here, let's move that to the top. And so you'll see that the E field for a capacitor now, you've got sigma over 2 epsilon naught plus sigma over 2 epsilon naught. That's sigma over epsilon naught. So for a plate capacitor, and we'll obviously get into capacitors a lot more significantly later, but this is one of those applications I'm talking about. Capacitors are used everywhere all the time, and we use them in all kinds of ways. And what we're saying here is that from the standpoint of an electron near one of the plates trying to move from one to the other, I guess we can consider the electrons over here, and they want to cross this gap, and we can use the fact that there's an E field between these two charged plates to store electricity, to move electricity, to halt the flow of electricity. It's got a lot of different implications. Okay, that's actually a really good way to do this. And in the next video, I think I'll walk through what it's like to have E field near a conductor and in a conductor. All right.